Hello everyone, welcome back. It's your math teacher, Mr. Boyden, working on a little bit of calculus today. And as we get into the winter season here, I want to remind you that if at any point during this video you start feeling a little bit cold, just look around the room you're in. Why don't you go over and stand in the corner? I mean, you know it's 90 degrees, right? All right, well, let's get to the calculus. Folks, today we're talking about volume of solids with Diss and Washer method. And first thing we should talk about is this word solid. Sorry about that joke, I just had to. So for volume of solids, I want you to be reminded a circle is a shape, right? Over here we've got an orange. An orange is a sphere, and a sphere is not actually a shape. It's three-dimensional, it has volume, and so if it's three-dimensional, we call it a solid. If it's two-dimensional, we call it a shape. Okay, so just want to make that distinction before we get started. The easiest way of thinking about today is we're going to be taking objects that have radial symmetry, meaning when you spin them, they have symmetry. So for example, this looks to me like maybe it's some sort of pottery. And if you spin that pot on a turntable, it'll spin around. If you had some function like this one and it rotated round and round and round and round, like if this is the y-axis of a graph and that's the x-axis, and I rotate it, it would make that same shape. Now notice this piece of pottery has been all chopped up into different rings. And here's why. Because we don't have a formula for finding the volume of a vase. However, look right here. What kind of shape did this get chopped into? Looks like it's probably a cylinder. If we have cylinders, we can definitely find the volume of a cylinder. And so by thinking of each of these sections as cylinders, we can then find the volume of the whole vase. And that's the basic concept of today. Same thing with an orange. With an orange, we're just going to cut it into a bunch of slices. Technically, we'd want to cut it into as many slices as we could. And you know what? I know that some of you are sitting there thinking, but wait, Mr. Boyden, that's a sphere. I know the volume formula for a sphere. Well, today we're going to pretend like we don't. Well, why? Because the way we learn math and the way we think of math is if we haven't proven something or if we haven't derived it, then we don't know it's true. It's very similar to the beginning of our derivatives lessons, where some of you noticed when we were doing the difference quotient, you said, wait a minute, every time we take a derivative, the exponent drops down by 1. And so you had noticed that, but until we actually could show that that was true, we weren't allowed to use that fact. We're going to do something kind of similar today. And so we're going to be finding those volumes. Now, one question that comes up with this is, why would you not just do the old science class thing and submerge it in water? Well, for a lot of objects, you can do that, but for some, you can't. Like, how about a loaf of bread, for example? You're not going to submerge your loaf of bread in water. You'd need an actual calculation. What if you're an engineer and you're building a building or you're building a bridge? You probably don't want to have to submerge the actual building or the bridge in water for a couple of reasons. Number one, you're going to need a lot of water and you're going to need a big crane and then you have to actually build it first. The idea would be we'd want to know the volume of something first so we know how much space does it take up and how much does it cost. So rather than building the whole building and then making a giant crane that's even bigger than the building and dipping it in a giant glass of water, why not just hire an engineer who can do this simple calculation that we're going to learn today and they'll find the volume and there you go. Okay, so that'll work. Now I want to go back to the beginning for a second. I intentionally chose an orange here. I intentionally did not choose a banana. Oops, that's the ugliest banana in the history of man, but it's a banana nonetheless. So why did I not choose a banana? Because when you spin a banana, or one student yesterday in class said it's kind of like shish kebabs, or if you put a skewer down it. If you put a skewer down a banana and you rotate it, it doesn't still look like a banana. If you put a skewer down the middle of this orange and you spin it, even if you spin it really fast, it still looks like it's an orange. Another analogy that I really like is like when you're jumping rope. If you jump rope really, really quickly, the person that's jumping the rope, it's kind of like they're in a little bubble. And that bubble has volume. That's a solid of revolution because you're revolving the jump rope. Okay, so that's kind of an intro to today. Let's get to the specifics a little bit more. Okay, and so here's what it is. When you cut it into all those little slices, you'd want them as small as you possibly could. It's the same idea when we did Riemann sums. We started out with big rectangles, and they weren't quite accurate. Well, what would we do if we wanted more accuracy? We'd make smaller rectangles. We'd make a little rectangle there, and we'd make a little rectangle there, and we'd make a little rectangle there, and the smaller the rectangles are, the more precise it is. We want the same thing. So on our orange, we want the smallest slices we can. And when we do that, each of those, if you get down to the point where you've cut them infinitely or infinitesimally thin, each of them is a circle. Okay, and so that's all this is saying here. We're going to add up, or we're going to sum up. Remember, that's a sum. We're going to sum up all of the areas of the circles. Okay, so we have the cross-sectional area of a disk. They call it the disk method, not the circle method. A disk is something circular, right? So each of one is a cylinder of infinitesimal height, and this is the thing we have to remember. The area of a circle is pi r squared. So what happens with this then? we get the integral from a to b of pi r squared dx. You'll want to add that to your notes. Okay, so with that, let's go and think about an orange a little bit. Okay, for us, we're going to assume an orange is a sphere. So when we look at it in a two-dimensional projection, because notice, we're looking at a computer screen. This is two-dimensional, not three-dimensional. What kind of shape do we have? And notice I didn't say solid, I said shape. Okay, we've got a circle right here. In order for this calculation, we're going to need a radius. So I'm going to use the same one I used in class the other day. We talked about having a diameter of 4 inches. And so that's what I'm going to use here as well. And then I'm going to go about this calculation. So we know the volume is going to be all those areas of the circles added up, and we just talked about knowing that the circles have an area of pi r squared. And so now we need to figure out how we're going to do that in this context. Okay, so this is a circle. We need to first remember what's the equation of a circle. That's x squared plus y squared equals r squared. We know our diameter is 4, which implies that our radius is 2. Now that's the radius of the sphere, so I'm going to plug that in here. And so I get x squared plus y squared equals 2 squared, which is 4. Okay, now let's come back down to our calculation on the right and see if we can figure out what that means. You need to remember that this radius right here is the radius of a circle. Circle, okay, yes, I can spell. But this over here was the radius of a sphere. Okay, so a mistake a lot of new learners make is they just say, oh, radius is 2, plug in a 2, off I go, this is easy, boom. No, it's because it's not that easy, and here's why. Because notice this circle right here, okay? This circle has its radius right there. There's lots of circles. I mean, there's another circle over here. This is the biggest circle. Maybe it goes to the middle. There's more circles. There's all these different slices of the orange, and each one is a different size. Think about that. If you chopped an orange up, just vertical slices, chop, 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 they're not all going to be the same size. So this is actually a variable. Now, it's not just random. We can assign values to it. Because look, the radius of this circle is right here. And on this graph, when we go up and down, that is a y value. So that y value is going to be the same as that radius. Now, why is that helpful? Because we have an expression here that relates the x and the y values and the radius. So let's solve that, because I'm going to do that in 2 steps. So I'm going to get y squared equals 4 minus x squared, and then I'm going to take a square root of both sides, and I'm going to get y equals the square root of 4 minus x squared, and that's plus or minus. Now here's the deal. That plus is the top side of the circle. The minus is the bottom side of the circle. Notice that's all negative y values. Okay, now I don't need both, because what I'm going to do, just like a jump rope, this is like the person's hands, here's the jump rope going over the top. That thing is going to spin, and we're going to make a 3-dimensional shape, or a 3-dimensional solid. Okay, so I'm not worried about the fact that it's positive and negative. That's my y value. We said right here the y value represents the radius of each circular cross-section. So what that allows me to do then over here is I can, instead of writing r squared, I can put square root of 4 minus x squared, and it's squared, so I'm going to put a little squared right there. Let's even out these parentheses. Oops, sorry. And don't forget the dx. Okay, what I'm going to do with this pi, remember pi is a number. I mean, I know it's a Greek letter, but in math it's a number. So I'm going to factor it out, and then we also need to get our bounds. So we're going to look back at our picture. We know that the diameter is 4 and the radius is 2. So what is this x value? Okay, that's going to be 2. What is this x value? That's going to be negative 2. So we're going to be integrating from negative 2 to 2 over this function. Okay, so let's do it. It looks a little scary, but it's actually going to be pretty simple, because look, we have a square and a square root, so cancel that out first. Okay, let's make it as easy as we can, and I'm going to come down to here so I have lots of space to work on what I'm about to do. So, okay, oops, I want to change my line thickness. Excuse me just a sec. Okay, there we go. So now what we have, we are going to actually integrate this, because that canceled out. Do we need a u sub? Nope. We know how to integrate 4, and we know how to integrate x squared, so let's do it. So what I get is I still have pi. My integrand is gone, because I'm integrating in this step, and I get 4x minus x cubed over 3. Don't forget your bounds. 2, negative 2. And now we plug them in, and we're going to be done. So let's do that. Okay, here's pi. Let's start plugging in our bounds, and I'm going to do mental math here, y'all. So 4 times 2 is 8, and I'm going to plug in a 2 right here, and 8 cubed is, or excuse me, 2 cubed is 8, so minus 8/3. Fundamental theorem of calculus says to put a minus and parentheses, so now I'm going to plug in a negative 2 right here. That's negative 8, and I'm going to plug in a negative 2 right here, and this gets a little bit exciting. Okay, I'm going to write this negative, Negative 2 cubed is negative 8 thirds. Okay, let's continue. I'm going to simplify as much as I can. What I notice right here is I have two negatives next to each other, so I'm just going to call that a plus. It's easier for me to think about. And I'm going to combine like terms. So I have 8 minus negative 8. That means 8 plus 8, which is 16. I have negative 8 thirds minus 8 thirds, which is negative 16 thirds. And don't forget the pi. Okay, and doing a little bit of fraction action here, I get 32 thirds pi. And then what are the units? Okay, because let's pause for a second. What did we just find? We found a volume, and our initial measurement was in inches, so this is going to be inches cubed. Okay, and that's it. So that's how we find the volume of our orange. All right, so that was perfectly nice coming up with the volume of our orange. But if the radius changed, we have to do a whole new calculation, and that becomes rather cumbersome. And so what it would be nice is if we had a way of quickly finding the volume of any orange or any sphere. Okay, I'm using the orange as a proxy to understand it, but we're really trying to figure out volume of a sphere. And so if we had an arbitrary radius, that's the situation I'm thinking about here. So do we already know a formula? Yeah, of course we do. We're going to show where that comes from. So what I'm going to do is I'm going to think about the visual of this. And it's going to be a semicircle that gets rotated around the axis like that and comes out actually off your screen toward you in the room, and it's going to make that sphere. And I know that the arbitrary or the general equation for that is x squared plus y squared equals z squared. Excuse me, not z squared, r squared. I guess technically z squared would work too, but let's do r to be specific for a circle. Okay, and we want to find the volume, so that's going to be a deal of pi r squared dx. And so in order to figure this out, we remember from the previous example that r, because we have those cross-sectional disks, the radius of each of those is a y value. So let's solve this thing for y. Now when I do that, I get y equals plus or minus square root of r squared minus x squared. Now, guys, if that's not making sense, pause the video and try the steps, okay? We're going to just do algebra steps to get that y all by itself, okay? And in this case, I'm looking at the positive version, so I'm going to be doing the positive, not the negative, okay? So I'm going to sub that in. This is kind of my side work. I'm going to box that off. I'm going to sub that in into here. So I get pi, and I'm going to bring the pi on the outside because it makes it easier for me. And then instead of r squared, I'm going to write square root of r squared minus x squared, and it's squared dx, and then we're going to need some bounds. Okay, now we said an arbitrary radius, and so I don't actually know the value of this right here. I don't know if it's 6 or 12 or pi, but what I do know is that this has a radius, and no matter where I put that on the circle, put it out like here, that's the radius. So that's negative r, and that's positive r. Okay, and I want to do a couple little algebra tricks before we get into the calculus. Now the first one is I have a square and a square root, so see ya. It's been fun. Bye. Go away now. The second one is going to be like this. Now up here, if you revolve this around the axis, you have two distinct regions. You have this one on the left, and you have this one on the right. And the question for you is, which one is going to generate a greater volume? Left side or right side? I hope you can see that we're cutting this orange directly in half right here. And so it's not that one side is bigger than the other, but what it is that they are exactly the same. So that allows me to do this trick. I'm going to actually change this into 0. And so what that means is I'm only going to be integrating from the origin to r. I'm only going to be catching half the value. I'm only doing this half. Now, if you're only doing half, that means this answer, it's going to be too small, isn't it? It's going to be half as big as it should be. So we are going to double it to compensate for that. And the reason I'm going to do that is it's going to make my algebra and my calculus a little bit easier now. So with that said, let's get on with the math. It's time to integrate because we've done our simplification. And here's where it gets a little bit fun. Notice that says r squared, but we're integrating with respect to x. They're not the same. So r squared isn't really a variable. You'd have to pick it in the beginning. You'd have to say, well, but I want r to be 5, or r to be 10, or r to be whatever. So that actually is just a number. And think back to the previous example where we had a 4 sitting there. What did it turn into? It turned into 4x when we antiderivatized. So the same thing's going to happen here. We're going to get r squared x. We're not adding and dividing. Well, technically we are because it has an x to the 0 next to it, and we're only adding and dividing to x according to this. Okay, don't forget the 2 pi in front. Okay, and let's go to the next one. This one is x. That matches x, so we are going to add and divide x cubed over 3. We're going from 0 to r. And let's go ahead and plug those in and see what happens. So I get a 2 pi on the outside, no big deal. Let's start plugging in r. R is plugging in where? Is it plugging in for x or for r? If you're not sure, go back to the original question. Okay, this is always dx, so we're going to be plugging it in for x. So what that looks like then, I plug in an x here. R squared times r is r cubed. Plug in an r right here, we get minus r cubed over 3. And then what happens when we plug in a 0? Okay, that'd be 0 times that one. Well, who cares? It's 0 times anything is 0. Plug in a 0 here, that's 0. So I'm not going to demonstrate the step here because I'm mentally doing a check. When I plug in a 0, those go away. Now I want to simplify this. R cubed minus r cubed over 3. If you're having trouble with this, give them a common denominator. And you get 3 minus 1. So that is 2 pi times 2 r cubed over 3. And then let's simplify that out. 2 times 2 is 4. We have a 3 on the bottom. And then we have a pi. And it looks like an r cubed. Now, do you recognize that? I hope so. You probably learned about that back in geometry or maybe in middle school or 9th grade or something like that. That is the volume formula for a sphere. And this is where it comes from. Okay, this is one way of understanding what that formula is. Now that we have that formula, we can use it if we want to. But that's why it works. Isn't that cool? I mean, it's not just random that we have these formulas. They all come from somewhere. This is one of the things that I love about math so much is there's all these little connections. And unfortunately, we don't always do a good job of showing you that early on in your math experience. We go, oh, here's the formula, kiddo. Here you go. But there's all kinds of really cool, beautiful connections like this that come up as we are learning. Okay, so for the rest of the video now, I want to help you get a little more comfortable with this process. We've got the concept down. We've shown what it can be used for. Now I'm going to show you a couple things that can happen, a couple tricks, and we're going to be done. Okay, so let's do this example. I really want to encourage you to pause the video here and try it on your own. Okay, here we go. This right here, first thing to notice, that's actually y. And that's important because y is the radius, okay, the radius of the circles. So when we go ahead and set this up, what we're going to have is, well, pi on the outside. We have our r value right there. I know it says y, remember, that's the radius. So we have 5 minus x squared with a square root and it's squared dx. All we need is bounds and we're off to the races. So it's really hard to tell by looking at this. I'm actually going to have to use the function. So I'm going to pull my function. I want to know this point and that point for my bounds. And notice those are the zeros. Hooray, that's easy to find. So we're just going to set this equal to 0. So square root of 5 minus x squared equals 0. Square both sides. You get 5 minus x squared equals 0. Let's add an x squared to both sides. So 5 equals x squared. And then when you take a square root of both sides, what do you get? X equals plus or minus root 5. Okay. Now, are these two sides symmetrical? Yes, they are. This is a circle. We have y-axis symmetry, so region 1 and region 2 have the same area. So what I'm going to do, I'm not doing plus or minus 5. I'm going to go 0 to 5, and I'm going to double it. Now, people, this is not a requirement, okay? You never have to do that, but I want to show you a trick to save you time because if you're in my classroom right now, we are preparing for an IB exam, and we want to be as efficient as possible. This is one way to do that, okay? We got a square and a square root later. Gosh, that's nice how that works out. And then let's integrate. So I get 2 pi on the outside. What on the inside? 5 turns to 5x. Minus x squared becomes minus x cubed over 3. And we have 0 and 5. Fundamental theorem, here we come. So I have 2 pi. I'm going to plug in, oh, excuse me, I've made a mistake. Okay, so guys, I hope you caught it. So I'm supposed to have a root 5 here, and I had written 5. Okay, so that's going to be confusing to me later if I don't fix it. Okay, so root 5, easy to fix still. I didn't actually screw anything up. It's easy to just put those roots on there now. But I was about to really screw it up. Okay, so now what we have, we've got 5 times root 5. Okay, that's easy. 5 root 5. And we're going to plug a root 5 in here. So minus root 5 cubed, root 5 cubed over 3. And we plug in a 0. Everything zeroes out, so I'm not going to write that. Okay, and guys, I'm totally okay with you leaving it here. I will show you one additional step if you want to learn how to simplify it, but if you wanted to leave it here, I would accept that for a test right now. Okay, so if you want to simplify, I'm just going to show you how this simplifies out. So the square root of 5 cubed is the same thing as 5 to the 3/2 power. Okay, and 5 to the 3/2 power is the same thing as 5 to the 1 plus 1/2 power. Because 1 1/2 is 3/2. And that means I can write this as 5 times 5, because I'm breaking this up to the 1/2, which is the same as 5 times the square root of 5. And the reason that would be relevant is because now it can match that. So that's my little side work for you on what I'm about to do. So now I'm going to plug that in. So 2 pi 5 root 5 minus 5 root 5 over 3. Okay, and now that I have those like terms, I actually do have the option to combine them. So I'm going to do that. And so I get 2 pi 5 root 5 over 3 and negative 5 root 5 over 3. In order to do that, I'm going to get a common denominator first. So that's now 15 minus 5. That would be 10 root 5 over 3. Make that look like a 5. And then I can combine my like terms. So I have 2 times 10 is 20. I have a pi. I have a root 5. And it's over 3. So if you wanted to know how to simplify it, that'd be a really good thing to do. Just if you want to practice the next level or something like that. I'd like you to know how to simplify that. As far as my tests, which are really quick and timed, right now I don't need you to demonstrate that. Getting to right here would be just fine with me. Okay. Again, I want to give you the option to try this one. Go ahead and pause the video and try it. What this is saying right here is that we have y equals square root of x. Okay, we're rotating around the x-axis. That matches what we've been learning. Bounds from 0 to 1. Pause, try it, see how you did. Okay, here's how it goes. Bounds from 0 to 1 of pi. Am I putting the 2 in front? Nope, because there's not two symmetrical regions and I didn't alter the bounds. I'm going to put a root x in here. Oops, x. And you got to square it, pi r squared dx. And this is going to go really quick, y'all. So when I cancel those out, I now can integrate. I get pi, x turns to x squared over 2. And I'm going to plug in a 1 and a 0, and watch how easy it is. When I plug in a 1 here, that is, well, we got a pi. I have a 1/2, so I'm going to just put that over 2. When I plug in a 0, it goes away, so I don't even need to do that, and boom, pi over 2, there it is, it's done. All right, 2 more things that can come up, and then we'll be done. So in this one, notice the difference in the question. Pause it and read it if you haven't had a chance to. In this example, we're rotating around the y-axis. We're not going around the x-axis. So I want to try to draw this and visualize and see if we can understand what it means. So let's see. The region generated by when you bound the y-axis. Okay, so y-axis, probably need an x-axis as well. The line y equals 8. The line y equals 2x. Around the x-axis. Okay, so here's my region. All right, and we're rotating that around the y-axis, so like this. Okay, and that's going to spin round and round and round. First of all, can you see what kind of shape that's going to make? It's going to generate a cone, because it's going to have the same thing over here, and it's going to be 3-dimensional. It's like a 3-dimensional triangle. It's a cone, because it's spun. Okay, so this time, the difference is, instead of chopping our shape vertically, our circular cross-sections are going to go like this. And so now, the radius is like that. Now, what would you call that? That's not a y value. It's moving left and right. That's an x value. So in this case, the radius is an x value. Okay, and that's going to matter because when we set up our pi r squared thing right here, when we're integrating, we're not plugging y in for that anymore. We're plugging in stuff that is an x value. So I'm going to bring this down. Right now that says 2x. That's no good. It's an x value that I need, not a 2x value. So I'm going to divide both sides by 2. And what I get is y over 2 equals x. So that is what's going in right here. Okay, so let's do our setup. And you know what? I realize I made a mistake. I hope you caught it. I put dx right here. But when we're going around the y-axis and our perpendicular cross sections are perpendicular to the y-axis, this actually needs to say dy. So I'll get it right this time. So I'm going to bring my pi out. I'm going to have a dy down here. I know that I'm going around the y-axis, so I'm using this right here. It needs to be equal to x. So y over 2 quantity squared. And I need my bounds. Now here's the catch, and people mess this up all the time. This is dy, which means these numbers, the bounds, have to be y values. Okay, so what are the 2 y values that bound this region? We got one down here at 0. We have one up here at 8. So we're going to be integrating from 0 to 8. To 8. And now our setup is done. And y'all, that's the hardest part because you already know the fundamental theorem. Once you get the setup, life is good. Okay, so let's do this. First, I want to simplify just a little bit. I'm not going to integrate quite yet. I want to square this. So I know that when I square it, y becomes y squared. 2 squared becomes 4. It's a number. I'm going to factor it out. 0, 8. Shall we chop the bounds in half and put a 2 out here? Probably not. It does not have any kind of symmetry along the axis that we are integrating over. We're integrating this way along the y-axis, and when I make a cut perpendicular to that, I'm not able to generate two symmetrical areas, so I'm not going to do that. Okay, and dy, and now it's calculus time, so let's do this. I'm going to leave my pi over 4 alone for the moment. I am integrating, so y squared becomes y cubed over 3. And I'm going to plug in a 0, and I'm going to plug in an 8. And actually, when I plug in the 8, that's interesting. 8 cubed is a big number. When I plug in a 0, that's 0, so we don't actually have to bother. So here I go, pi over 4 times 8 cubed over 3, and I'm not going to do mental math on that just yet. I do want to show you a trick to simplify that, though. And you know what? Maybe you want to pause and try to come up with one on your own without using a calculator. I think you probably can do it, but if you want to see how I do it, then hit play and let's see. Okay, so what I'm going to do for this is I'm going to write this out, and I'm not going to write what it is. I'm going to write a way of understanding it. So I'm going to write 8 times 8 times 8, and I'm going to write the 4, and I'm going to write the 3. And I'm going to start combining things that I can. And so I know that that right there, 8 over 4, that's 2. And so when I write my next step, I'm going to have 2 pi. Right here, I know that 8 times 8 is 64. So I've broken it down into easier numbers, and I know that I'm dividing by 3. I know that 2 times 4 is 128. And that's a pi, and that's a 3. And then the question is, can I divide that anymore? Nope, I can't. And here's how I know. Because 2 is not divisible by 3, and 64 is not divisible by 3. Therefore, their product, it can't be divisible by 3. That's impossible. Okay, so this is totally done. Okay, now we need to talk about something called the washer method. So for this, we're going to be given 2 functions. And the reason it's called the washer method is when you cut this solid, it doesn't generate disks, it generates a washer. And what I mean by a washer is like when you're, screwing in a bolt or something like that, a washer. All this section is there, and the inside's a hole, or it looks kind of like a donut if you chopped it. Okay, so we've got our functions, the functions y equals x and y equals x squared, and we've seen a very similar example to this, and we had to find the area between the curves. Similar idea, except this time we're finding a volume generated by rotating that area between the curves. So we already know that y equals x looks like that, and we know that x squared looks like that. And folks, if you didn't know, then here's what you can do. First, find their point of intersection. You do that by setting them equal. So x equals x squared. You could subtract the x over, and what you would have is 0 equals x squared minus x. You can factor that, and x will factor out, and you get x minus 1 left over when you do that. And so our zeros are 0 and 1, 0 and 1. Tick mark is what I meant to put there. Okay, and then if you test any number in the middle, like say 0.5, we'll know which function is the top function and the bottom function. So let's do the math together. If you plug in a 0.5 right here, you get 0.5, pretty easy. If you plug in a 0.5 right here and square it, you get 0.25. That's less than 0.5. That means x squared, the quadratic, is the lower function. Okay, so we've already found this area before. What we're going to do now is we're going to think about this as being a shape that gets rotated. Okay, and so that upper function, if you rotated it, it would make sort of a cone, and then the inside of it is going to be hollowed out a little bit. And so this is going to be our volume with something missing. So a volume minus some other volume, and that's how I want you to think about this. We have a volume, maybe a big volume minus a smaller volume. Okay, maybe something like that. Please pardon my handwriting, but you heard what I said, I hope. Big volume, smaller volume. Okay, and so what that means is we're going to do actually 2 calculations. So to find our big volume, which function is going to generate the bigger volume? Well, it's y equals x. It has higher y values. So what we're going to do is set up our integrand from 0 to 1, as the picture indicates, of the function x. And remember, it's a pi r squared thing, okay, because we're finding that volume. That's the big volume. Minus, it's that same minus. The smaller volume, smaller volume is generated by this lower function. And so we're going to integrate, same bounds. It'll always be the same bounds on this, by the way. Pi, then the function squared. So x squared, that's the function, squared. Okay, and that's our setup. I do want to show you a trick how to make that a little bit easier to work with. You can combine those as one integral. So that would look like this. Pi times the integral, from 0 to 1 of x squared minus, that's now x to the 4th dx. Okay, so now that we have our setup, that was the hard part, and that was challenging. But now that we have the setup, it's just straight calculus. If I had given you this probably a week and a half ago, I think you could have done it. So let's see if we can get through it now. Integrating, don't forget the pi. X squared turns into x cubed over 3. X to the 4th turns into x to the 5th over 5. Don't forget the bounds. Okay, and let's plug them in. Plug in a 1, I get 1/3 minus 1/5. When you plug in a 0, you get nothing. So I'm not going to do that. Okay, pi. I think I'm going to get some common denominators here, so I'm going to multiply by 5, and I'm going to multiply by 3. This is the old algebra trick to get common denominators. And so now, using a little bit of mental math, I have 5 minus 3, so that's 2. And then 5 times 3 is 15. And don't forget the pi. Okay? So the washer method is very, very similar. It's the same exact idea. All it is that you have some hollowed out area in your shape. And so, yeah, you're finding a volume the exact same way that we've done previously. The only difference is you need to subtract out that empty space in the middle. Okay? Hope you enjoyed the video, and I hope this helps you as you get through your work. I'll see you next time. Bye!